Let's talk a little bit about gases. So gases have no specific volume. They will fill their entire container, so they don't have a set shape. They'll just take the shape and fill up the volume of whatever container that they're in. And because the gas particles are so far away from each other, we assume that there are no attractive forces in between them because they're just too far away. We also assume elastic collisions so that when they do hit each other, they will just bounce off each other without losing any energy at all. And gases are dramatically influenced by temperature and pressure. So that is going to be an important variable when we look at these gases. Let's talk about standard temperature and pressure. It's also known as STP. So standard temperature for gases is really cold. It's 0 degrees Celsius. Now throughout this whole unit, do not use degrees Celsius. So always use the absolute temperature scale or the Kelvin scale. So 273 Kelvin is standard temperature. So anytime you see STP or just ST, you know that that means standard temperature. And so you know that it's 273 Kelvin. So how do you convert from degrees Celsius to Kelvin? So just a review, take your degrees Celsius and you're just going to add 273, that number to it. I always remember King Kelvin. So Kelvin is always larger. So if I'm in degrees Celsius, then I want to make my number larger. And if I need to convert from Kelvin to degrees Celsius, then I need to make it smaller. So I would subtract 273. But there's your formula. Kelvin is degrees Celsius plus 273. So in a previous unit, we had thermodynamics, a standard temperature of, and this one is incorrect on the slide, of 298. So that is 25 degrees Celsius. That's thermodynamics. So don't use that standard temperature. So gases, again, they are cold, 273. Also standard pressure. So if you ever see a SP, or that is the STP shortened to just standard pressure. It would be kilopascals, atmospheres, millimeters of mercury, or torr. And you need to know that these are all equal to each other. So we use kilopascals in the lab, and all the rest, it just depends on the problem, which one that we're going to be using. So make sure you pay attention to what unit you have, but anytime you see these units, kilopascals, atmospheres, millimeters of mercury, or torr, those are pressure units. Let's talk about Boyles Law. So in Boyles Law, the temperature stays the same. And we look at the relationship between pressure and volume. And Boyle, he noticed that there was an interesting relationship between pressure and volume. So pressure times volume equals some sort of number. And so let's say in our example here, our constant is 20. So what would happen if you doubled the pressure? So now it's 1 atmospheric units. Well, your constant is still going to be 20. So what number would fill in that relationship? Well, if you double your pressure, your volume goes down by half. So I would cut that down to 10 liters. So we see that as the pressure goes up, the volume goes down. So this is an inverse relationship here. And let's go ahead and do it again. Let's say we take our pressure and we double it. So now we're at 4 atmospheric pressure. We would predict that our volume would cut in half again. So we would have 5 liters. So altogether, that would equal 20. So I could take these numbers and I could put 1 on one side and 1 on the other, and I would get the same number. 20 equals 20. And this is Boyles Law. So in Boyles Law, this is a little bit small right here, so let me rewrite it. We have pressure times volume of our first situation is equal to pressure times volume of our second situation. And they're related to each other. So let's look at our situation 1 right here. So we have our molecules, they are hitting the sides of the container, and when they collide with that container, they exert a pressure. And then let's see what happens when we cut the volume in half. When I cut the volume in half, I get more collisions. Because I get more collisions with the sides of the container, the pressure will go up. So again, if our volume goes down, our pressure goes up. So this is an inverse relationship. Now, these are story problems that we're going to be having. And they can be really confusing because there's a lot of numbers, but you need to look at each number and figure out if it's a temperature unit, pressure unit, or volume unit. And with Boyles Law, we're just looking at pressure and volume. But let's go through and identify what each of the numbers are. So in this first number, 100 milliliters, this is a volume unit. And because it's my first volume unit, I'm going to call my V1. And this next number is a pressure unit. And they will go together. If you read the sentence, 100 milliliter sample of air at 100 kilopascals. So those two values go together. So that's my situation 1. So now I'm going to transfer it to a different container. And so this is my second volume. And that says, what is the new pressure? So I don't know the new pressure. So write Boyles Law, P1V1 equals P2V2. And I need to solve for P2. So you can put your numbers directly into the formula as is and just make sure you follow the algebra rules. But I'm going to manipulate this equation. So I want to keep P2 and get it all by itself on one side. So I'm going to divide each side by V2. And that will cancel out, and I will have P2 equal to P1 times V1 over V2. And I'm going to go ahead and substitute those numbers in. So P1, we have 100 kilopascals, and V1, we have 100 milliliters. And that's divided by our V2, our 25 milliliters. So notice that my volume units are the same. So they will cancel out, and I'll be left with a pressure unit. And so my answer ends up being 400 kPa. And let's look at sig figs. So we have 3 sig figs in the first number, 3 sig figs in the second number, 3 sig figs in the third number. So when I'm multiplying and dividing, you want to go to the lowest number of sig figs. So I should have 3 sig figs. So I'm just going to put a little decimal right there. So that means that we've measured to that ones place. So this is our new pressure when we put it into a smaller container. And it kind of makes sense. If you look at this, we see that our container was cut in half by 1/4, and so our pressure goes up by 4 times. So this should be question number 19 from the homework, or at least a problem that's close to question 19. So look around in your homework and just try to match it up. And let's go through and look at our different terms here. So we have 100 liters. So this is a volume, and it's my first volume, so I'm going to call it my V1. And then here's a pressure, P1. And it says what will be the volume. So I'm solving for a second volume, and there is my second pressure. So again, start with your formula, P1 times V1 equals P2 times V2. And this time I'm going to solve for V2, so I'm going to divide each side by P2. Again, if you do not like rearranging equations, then just go ahead and plug it into the Boyles Law equation. You're going to get the right answer as long as you follow your algebra rules. So let's plug in each number. So my P2, or excuse me, my P1 is 500 kPa. My V1 is 10 liters. And my second pressure is 702.6 kPa. My kPa is going to cancel, and I'll just plug this into the calculator. And I get 7.116, and my units is liters. Let's look at our sig figs. So I think our smallest number of sig figs is 3, so I'm going to have that 6 round that 1 up to 2, so 7.12 liters. Okay, so Boyles Law with pressure and volume is very important when you go scuba diving. So when you go deep under the water, you have a lot of water above you, and so your pressure increases. So remember, as the pressure increases, then the volume of gases go down. And in your body, you have dissolved gases in your blood. And so it's okay descending, but when you come back up, what's going to happen? The pressure is going to go down, and now the volume of those gases is going to go up. If you ascend or go up to the surface of the water too quickly, the gases that are dissolved in your blood, they will actually form little bubbles of gas in your bloodstream. And those bubbles will tend to congregate at your joints and cause a lot of pain. It's known as having the bends, and you actually can die from it. So if there's some sort of emergency and you have to get up to the surface, and this has happened, like people have run out of air in their air tanks, and so they just ascend rapidly, they end up passing away because their bodies just can't take this rapid change in pressure. So if you do scuba dive, you have to come up slowly. And as you come up slowly, that your body is able to blow out that extra air, that increased volume that is going around in your body, and so then you can survive the experience. So ascending very slowly in scuba diving is very, very important.